Hey, happy Monday to everybody. Hope everybody has a good time these Thanksgiving holiday and these two digital days. So our first introduction to rational is I'm just looking at this Desmos graph of a rational function. And if you take a look, the one that I've graphed over here is the one that is highlighted in red, and it says 2x plus 5 divided by x plus 3. First thing I notice is when x is negative 3 in the denominator, my function is undefined. And then we will remember that's where we have this vertical asymptote at x equals negative 3. You can see that on the graph, that vertical line that splits my graph up into two separate functions. Second thing that I notice is that I have an x-intercept and it looks like about negative 2.5. Remember, when we have a fraction, when the numerator is 0, that is when I have a output of 0. So if I look at the top of the fraction 2x plus 5, if I set that equal to 0 and solve it, because that's where my y would be 0 or the output, then I notice I would get negative 2.5. I would subtract 5 divided by 2. Negative 5 divided by 2 is negative 2.5. So our denominator is going to get us vertical asymptotes or points of discontinuity, and our numerator will get us x-intercepts. Also notice that this has a horizontal asymptote. It looks like if the y-intercept is 1.667, and it looks like at 2 there's a horizontal asymptote that both sides of our graph are approaching. And horizontal asymptotes can be crossed, but what they do is they determine end behavior. Remember, when we do end behavior, we're looking at the furthest right and left parts of the graph. And if the furthest right part, right where it gets off the screen around 10, 11, 12, 13, 14, over here, you notice that it's approaching 2. That would be its end behavior. So it's not infinity, it's not negative infinity, it's approaching the asymptote of 2. And if you look on the left side of the x around negative 16, 17, 18, negative 19, notice that it's also approaching 2, and that's what its end behavior would be. So the horizontal asymptote determines end behavior, where the vertical asymptote is where my function doesn't exist because you cannot divide by 0. And that leads us to our very first INB. We've talked about vertical asymptotes before, and we've talked about x-intercepts on the rational graphs, but we haven't talked about how can we find a horizontal asymptote. So there are three cases, and it's very easy to do. You're just going to look at the degrees of the two polynomials. On case one, notice that this top polynomial is a first degree, and that my bottom polynomial is also a first degree. So this case is going to be when the polynomials, the one in the numerator and the one in the denominator, when they are the exact same degree, that's going to cause a specific horizontal asymptote. So these are where the numerator and denominator degree are equal. Okay, and the horizontal asymptote is going to be the leading coefficient divided by the leading coefficient of the denominator. Remember, the leading coefficient is the number in front of the term that determines the degree. So on my very first one up here, the leading coefficient is a 1, and the leading coefficient of the denominator is a 1. So overall, my horizontal asymptote would be at y equals 1. My second example, my denominator again is a first degree, and my numerator again is a first degree. And these are just, they don't both have to be first. They could be both second degree or third degree or whatever, it doesn't matter. But once you realize that they both have the same degree, then what you're going to do is look at their leading coefficient. So this one is 3 on the numerator, and on the denominator it's 1 again. So this one is y equals 3. Okay, so same degree, you need to think leading coefficients. Okay, case 2 is what happens if the degree of the numerator is less than the degree of the denominator. So notice this one's a first degree, this one's a second degree. Again, they're not always have to be first and second degrees, and they don't have to be one off. If the numerator was a first degree and the denominator was a fourth degree, then the numerator would still be a smaller degree to polynomial than the denominator. And my denominator is the second degree. So it doesn't matter how close they are in degrees, they could be one off or they could be five off. As long as the polynomial in the numerator has a smaller degree than the denominator, your answer is always going to be y equals 0. Okay? Always y equals 0, which is a nice one. Because the first one, even though that wasn't hard, it was the degrees of it's the leading coefficients divided by each other. It's nice where it's just one set thing. Okay, case 3, when the degree of the numerator is greater than, right? There is no horizontal asymptote. But what there is there's a slant asymptote, or it really doesn't matter. It just depends what happens when you divide the two function. Whatever equation that you're left with is the asymptote. So on the top one, we have a degree 2, and on the bottom, we have degree 1. So we know we don't have a horizontal asymptote. So if it asks you, does it have a horizontal? The answer would be no, but it does have an asymptote. What you have to do is you have to divide the two polynomials. So I'm going to look at polynomial A, and I'm just going to divide these two. Put a 0x in because I'm missing that term, and I'm just going to say x times x is x squared, x times 2 is 2x. I'm going to subtract minus 2 plus 2, then I'm going to say times 2, get my negative 2x minus 4, change my signs. We don't care about the remainder. Even though I got the remainder, the asymptote of this equation is y equals x minus 2. Doesn't matter if I get a 0 remainder or if I get a remainder of some funky output. Doesn't matter. The asymptote is y equals x minus 2. So it's a linear asymptote. And we'll take a look at that here in a second. So B would look like x squared minus 1. This one you would definitely have to long divide, where the other ones I could have solved for 0 and synthetic, but since this is a quadratic, this one had a lot of zeros. Okay, so I'm going to do what, x squared, and I get x to the 4th, and then minus x squared, change my signs, just in case if I have a 0, a cubic, and then what do I get? Negative 3x squared, 0x squared. And so again, I'm going to want to multiply to get this negative 3x squared. So this would be minus 3. I can stop there knowing that I'm not going to go any further, right? I'm at my constant term, have my negative 3x squared, and I have a plus, change my signs, remainder, whatever. It's not about the remainder. My asymptote is a quadratic. So if I graph this quadratic, right, it just went down 3, over 1, up 1, over 1, up 1. This would be my asymptote. That this function, this rational function, will be approaching in some way. Okay, so not hard to find. Definitely the degree 3, the case 3, where you long divide might be a little bit funkier. but you just have to kind of long divide. Let's take a look at Desmos of these separate situations. Okay, so first one here is the same degree. Notice that the leading coefficient was 2 over 1, and so I had a horizontal asymptote at 2. The next one, notice that I have a degree in the numerator is the first degree, the degree in the denominator is the second degree, so the horizontal asymptote is at y equals 0. This is a good showing that you can cross a horizontal asymptote. There it is at y equals 0. Have a x-intercept at -1, but notice my end behavior, the ends of my graph, all the way to the most right, that graph is going to 0 on the right, all the way to the left around -15. It's approaching 0. So it defines end behavior, not a place of crossing and not crossing. Okay, my last one is when I have a slant asymptote. This is a pretty good one. You can see when I divide these two, I'm going to have a linear asymptote that is going to go somewhere right through, if you can see my pen a little big, right down there, definitely. I guess we could divide these two and find them, but I didn't do that. So anyways, there's a diagonal asymptote that you can see. It looks like it have a y-intercept of -1, maybe a slope of 1. And so we could take a look at that. What did I say? A y-intercept, a slope of 1, and a y-intercept of 1. Might not be perfect. So -1. I was obviously a little off, but pretty close. Anyways, that's what an asymptote. That's the asymptote I'm talking about. I was just a little bit off. Okay, so the next INB, we'll talk about putting it all together.